a reference study simulation. This is not a production benchmark. This was performed at our like non-production settings. So this is where where my practitioner perspective matters. So in a regulated environment, the model is not just like data science artifact. It becomes part of the control panel. It can influence detection, alerting, case prioritization, incident response, and customer impacting decision. The question becomes now operational, like who trains the model, what changed, was the update protected, did the model drift, can we explain the decision path, and can we roll back with service instability. The goal is not just like higher accuracy, the goal is like resilient, auditable, and recoverable AI. So coming to the final slide, like a call to action. So my call to action is practical, like do not start with like open-ended data consortium. Start with one thread class like fraud velocity, account takeover, or intrusion telemetry. Define the trust contract, like where does the data stay locally. Update rules that are explicit. Audit the evidence that is written, and opt-out paths are should be very clear. Then pilot with 3 to 5 institutions using like non-production telemetry first. Measure utility and leakage risk. Optionalize operationalize it like a platform with a model registry, and then release gate, drift checks, rollback playbooks. Only then scale with regulatory ready evidences. Incident response, integration, and a clear considered cadence can drive the next strategy. So in this way, we can build the next generation of like financial cybersecurity that can collaborate by design and privately by default. So I close this thought like we don't need to centralize trust to collaborate. We need to engineer the right privacy, resilience, and government controls around the shared learnings. Here I conclude my talk. Let me know, guys, if you have any questions for me.
Sure. Are able to see my screen? Okay, thank you. So, uh, thank you very much, ICCC Nate, for inviting me for this topic. Myself, Rakesh Moore, I'm a program lead at AJ Gallagher, USA. And today's my topic is building trust in smart environmental system, a safe, explainable, retrieval augmented generation based approach to renewable energy forecasting. I know that it is a little bit a different topic, but you know that every company nowadays is coming up with the more and more powerful model, uh, AI model, and powerful model need the compute or processor like higher CPU, GPU, and that required the more and more energy because they are coming up with the data centers, and those data centers are huge nowadays. So electricity demand is exponential increasing day by day. So how we can leverage the renewable energy so that we can provide whatever we need uh, into the electricity to perform fulfill the electricity demand basically. But when we talk about the renewable energy, the problem with renewable energy is that it is dependent on environmental thing. It's not dependent on us. So that's why the forecasting is really important here. So let's see how we can give the more reliable forecasting using RAG, that is retrieval augmented generation, that is the AI method, and why the traditional method is not suitable. That's what I wanted to share here. So we'll start our study basically uh, um, like uh, examining the forecasting uh, imperative or current model limitation, then we'll see the framework with four phase, that is the RAG retrieval, LLM generation, guardrail, and then the explainability, and then we'll conclude with the result. So moving from agenda to core topic, so accurate forecasting is not just a technical pursuit, but it's a practical necessity. Why? Because the fluctuation of renewable energy bring grid instability, economic penalty, and financial stake. Like inaccurate day-ahead prediction uh, cause a significant financial market penalties. As per the study, there are 400 million annual imbalance cost in California Independent System Operator, that is a CAISO, from solar forecasting error, and it's a huge. And one study with right hand side, you will see that if we reduce a reserve requirement, so if study have shown that like optimizing day ahead forecast can reduce the reserve requirement by 30%. So here our main goal is to for is to how we can uh, forecast renewable energy properly. So forecasting is an operation problem, not just a machine learning problem. And this is the main uh, goal of this study. So let's jump to see what are the limitation of existing deep learning model. So we saw just now, I was trying to explain the value of accurate forecasting, but the existing deep learning model are face obvious bottleneck. They are complex in architecture and lack transparency. Another one, trusting a critical automated decision is very difficult. Suppose that if a grid operator is sitting and seeing the screen, like how many uh, gigawatt energy I need for next 4 hours. Suppose that if it is less, then I need to explain or I need to give the warning to the CT, or to a particular function or particular company, that you are going to get a less energy. Um, but but as I say that our model is kind of a black box, so he will not get a correct decision. Another thing, those existing model failed catastrophically during extreme weather system, and sometimes they will create the unsafe prediction. So basically, the main message that we need a model that are grounded, constant, and explainable. So we require a particular thing which model can get a historical data, like historical context, enforce the physical safety boundaries, and then deliver the explainable side. So let's see how we can get that. But before that, uh, I'll try to explain what is RAG, like retrieval augmented generation. Like retrieval augmented generation is a kind of method where the large language model integrate with the external knowledge source during the response generation, so that we'll get the accurate and the knowledge based uh, information. Like the key benefit is factual accuracy, knowledge freshness, and transparency, and that help to reduce the hallucination by 32 to 47% as per the study. So how we can utilize this RAG into this our framework, that is our next see. So here we are proposing that RAG safe forecast model, where we wanted to integrate the RAG, that is the retrieval uh, augmented generation, to fetch the historical context, and then it will go to the LLM generation, that is the we are proposing to use a temporal fusion transformer, that is a TFT model, and it is a powerful deep learning model developed by Google specifically for this kind of forecasting. So we are proposing to use this one. Along with that, a three-tier guardrail, where to verify the result or evaluate the result generated by LLM, and then the explainability layer, like using a sharp and natural language output. The sharp is a analytical tool basically, which generate the more accurate prediction. So let's deep dive into the one by one quickly. So how we are suggesting, like moving into the our first layer, that is the RAG architecture retrieval. So RAG architecture retrieval, uh, so we are feeding the current weather forecast and grid variables are from as an input, and then RAG with as a RAG, it will go to your database to get some historical scenario and from the vector database. After that, extracted data as well as the real-time parameter will be given to the uh, prompt, so that prompt can be augmented or create a new prompt, and it will give to the model, and that model is the LLM model. Uh, so key idea is the similar past condition provided useful guidance for the present. Like it's not a black box. Like when what is the condition based on the data, and based on this condition, the past data what we did, that data we can pass it to LLM. Once the LLM get that data, like we are saying that the TFT, this is the second layer, the context retrieved by RAG, and it's fused with historical data, and then through multi-head attention. So, and then we can provide the multiple uh, parameters like a GHI, like the global horizontal irradiance, that is the total amount of solar radiation received by surface strictly horizontal, and along with that some parameter like the temperature, historical power, wind speed, and then the humidity. With the based on that, LLM can generate the prediction. But it's not like that whatever the prediction is generated by LLM, it's we can take it blindly. No, so we are going to put there a guardrail. That is the three types of guardrail we are suggesting here: that physical guardrail, logical guardrail, and statistical guardrail. Physical guardrail, basically it's to block the impossible value like the negative power energy, so that will take care. Logical guardrail is apply rules such as uh, like solar power equal to zero at night to check that one. And then statistic guardrail is to prevent unrealistic jump from ramp bridge. So with the help of this safety check, we need to do before forecast reach operator. And at the last, with the help of explainability layer, we want to generate the forecast which is in the normal humanized language. Like it's not like we just saying that the output is 120 megahertz. No, so if you see the right hand side, it should be a natural language generation, like the output is 120 megahertz. Why? That is the very important thing. Why? Is because it's driven by high GHI and low cloud covers, so that whoever the operator seeing that, he can understand why the power, the next 3 hours the power is generated 120 megahertz, and then the what is the factor behind that. And if you see retrieval, retrieve historical analogs. And so basically we want to give the more reasoning so that operator and everyone can trust on it. So here is the high level architecture what I was explaining, that first will be data ingestion, that is the live weather feed, then the vector retrieval getting a historical data, then the LLM generation, that is the LLM augmentation, creating a prompt and getting a data. Then next is the initial forecast from the LLM, and the fifth is the validating that forecast using a guardrail, and then the last is explainable output. So we tested this thing against the synthetic data, the data which is available on the open source market, that is CAISO market data and open metro weather data with the 15-minute resolution, and results are really good. If you see, we saw the overall MEA reduction and then the extreme weather gains. Uh, uh, like whatever, it clearly show that RAG's safe forecast improve MAE over the baseline model. And this is all synthetic data. We didn't get chance to check it on the real data. Uh, and this is the uh, another result where how safety gain. So we are seeing that 99%, 99.2% total safety violation are reduced because of guardrail. And this is the practical deployment process. Like we are suggesting, like get the data like vector API and weather API vector database from SCADA sensor. Use that rack safe force service as a REST API, and then generate the output and pass it to grid. uh, with that one, I'll conclude my like presentation with the key contribution with this study as that MEA reduction to rack integration effectively retrieve the optimal historical weather context and reduce the MEA. And the main important thing is safety violation drop, and then actionable externality. That is the very important for operators. So thank you very much for listening to me. If you have any question, I'm open to that one. Thanks.
Hey, is there another Sandeep that you're looking for? Sandeep, right, your last. There's another Sandeep. Okay. Can you hear me? Hello, can you hear me? Yeah. I don't know if there's another Sandeep that you're looking for. I'm Sandeep Raichura. Were you referring to me, Asta? Okay, thank you. Let me go ahead and quickly share my screen. Is my screen visible? Okay, great. Thank you. Thanks everyone for joining. I'm Sandeep Raichura. My topic is automating and scaling VM workloads with Azure Image Builder and Azure Compute Gallery. And thanks for the invite to be an esteemed speaker at this ICCCNet event and at the Manchester Metropolitan University, UK. With that, I'll dive right into the topic. And I will. So as you know, I am Sandeep Raichura. I'm a senior product manager at Microsoft, and I work on Azure Compute Gallery, Community Gallery, and Direct Shared Gallery. And here's my LinkedIn profile in case you would like to connect. Here's the agenda. Give a brief history of VM images. Why do image pipelines break? What should the pipelines look like? How does Azure Image Builder help? How does Azure Compute Gallery help? And then what does it look like end to end? Before we dive in, just a quick brief history of all the different images that we have available on Azure today. We have platform images. Essentially these are the vanilla images that everyone uses to deploy resources. These are available on Azure. Anyone that wants like a plain vanilla image goes to Azure Marketplace, picks up the image and deploy resources like VMs and as well as scale sets. There are custom VHDs. Essentially, these are lift and shift, bring your own blob, where you can bring your own data from on-prem and upload it to Azure and then start deploying resources. These are regional resources. Essentially, when you bring it in, you essentially have one single VHD to work with, and it is available only in single region. And if you want to deploy in other regions, you have to copy it over to another region. So, and we have also had something called as managed disks. These are an evolution of VHDs, but essentially these are like the snapshots that are created behind the scenes. These are also regional resources and not scalable. So with one disk, you can only create one VM or a scale set. And next up, it's managed images. Obviously, these are images that will allow you to scale. Essentially, when you have images, you can deploy multiple VMs at scale using an image, but these are single region resources. Essentially, what that means is that, if you want to deploy once, publish an image once, but deploy resources at scale across multiple regions and clouds, there's a limitation with managed images. And then finally, we're going to talk about compute gallery, what it is, and it's the evolution of all the images. And then essentially, this is what we offer today on Azure, which will allow you to scale your resources across regions and as well as share between the organizations. Moving on, now the problem isn't about creating an image, it's managing at scale, right? And rolling out as quickly as possible to keep the workloads secure, right? Now, in the world of AI, this is very important because you want, as new vulnerabilities are found with mythos and things like that, you want to ensure that you want to automate your image build pipeline as much as possible. That way, it can be rolled out safely to keep your workloads secure, right? And why do image pipelines really break at scale, right? Mainly because the problem isn't about creating an image, it's about managing it at scale, essentially, right? And you, when you have like manual creation of the image, it doesn't really scale, and you wouldn't have any versioning discipline, patch drift, and security correct gaps. Image sprawl across regions, and when you make a single mistake with an image, it's going to impact thousands of VMs, right? And so this is why the image pipelines actually break today. So if manual image workflows don't scale, how do we really build images in a repeatable, reliable way, right? Now, the best way to do that is, I mean, let me first show you what the image pipeline should really look at, right? So you take a source essentially, right? So there are like 5 critical steps in the, and no manual intervention in this critical path, right? So you have a source. A source could be anything. So you take an image from Azure Marketplace, or you use your custom source from GitHub or whatever, and then you apply your own customizations with scripts, security updates, and whatnot, and compliance hardening. And then you validate that by running automated testing and compliance checks to ensure that the image meets the organizational standards, and globally distribute the image so that once the image is ready, you want to distribute it across all the regions for scale. And finally, provision VMs and scale sets at scale using that image, because the image is already validated, and roll it out safely across all your workloads, right? So the goal is a fully automated loop: build, validate, version, distribute, and deploy with no manual steps in the critical path, right? Now, the session, essentially, I'm going to talk about how you can do that, right? Uh, let's move on. So how do you really standardize and automate the end-to-end process, right? Uh, Now, this is where Azure Image Builder comes into play, right? So you essentially, what you do is you automate the image by define an image creation through a declarative template. So you create a template where you say that, hey, here is my source. This is my source image, right? And then you add a customization on top of it, wherein within your template, you define what additional customizations and configurations you would like to have. And finally, you could say that, hey, once the custom image is customized, you want to add some additional validation steps in between, which will actually allow you to validate the image for quality. And finally, you can distribute the image through your pipelines to say that, hey, I want the image to be published across regions to deploy at scale. So this is how it all fits in. Now, once the image is built and validated, the next question is, how do you really manage it, right? So you've created the pipeline. You actually have a template that is automated, wherein what it essentially does is that as and when a new version of an image is published, your pipeline would actually pick up that image. There's something called as triggers in image builder. What it does is And once you set it up, you all you have to do is just set it up once. And what triggers does is every time there's a new version that gets published on marketplace, it triggers your pipeline and kicks off your image publishing pipeline and distributes the image safely. So all you do is you just set it up once, and then the publishing happens every time a new version of the source is updated. So that way you're not really, it's a completely touchless operation on your end, right? So now that we've talked about image build and validation, now let's see how you can manage it, version it, and roll it out safely, right? So this is where Azure Compute Gallery comes into play. Now, Azure Compute Gallery, formerly known as Shared Image Gallery, is a custom image management solution that allows users to manage their golden images created from standard vanilla images. Now, you're probably wondering why do you really want to create a custom image, right? When you already have like marketplace images. Now, that is fair, but large enterprise customers wouldn't really, doesn't really meet their compliance and security requirements. And essentially, enterprise customers want to add additional customizations like adding additional software or packages besides just taking a vanilla image, so that they want to, and also create a CIS hardened image. So that way, the image is much more secured and meets their compliance requirements for their organization. So which is why you need a custom image solution. So once the image is built, essentially Compute Galleries is what will allow you to replicate the image across regions, and which can be used to deploy VMs or scale sets at scale, right? So it is one of the most extensively used images across Azure, supporting over 180 million active cores. Additionally, ACG supports other artifacts, including VM apps, artifacts like gallery scripts, and as well as new artifacts that are coming in the future. Uh, Now, let's look at the value proposition, right? Now, ACG delivers critical capabilities like management. So you can version, you can add a custom publisher offer SKU on for the image. You can scale to thousands of VMs and scale sets. You can share the image across users, groups, regions, subscriptions, tenants. And if you want to share it publicly, you can do something called as community images, which I'm going to talk about. And then these are highly available resources, so you can share, store these images in ZRS, storage account, so to protect against the zonal failure. So in case a zone is down, the image is still accessible because the image was stored in a zone redundant storage. So these are some of the value propositions of Azure Compute Gallery. Now, how you set that up is you create a container called a compute gallery. Essentially, that's the top level container, and then you create an image definition. That contains the metadata, that is where you specify what kind of an image you want, whether it's Windows, Linux, what kind of a Hyper-V generation, what kind of a security type you want, and what features does it support, like accelerated networking, SCSI, NVMe, and things like that. Once you do that, you publish an image, and now image is what you use to actually deploy the VM. So this is the image version is the actual image, but then everything is defined by the image metadata. So for example, if you in the image definition, you set up a if you say that okay, it can host Windows images, you cannot put in a Linux image in it. So if you want to deploy a Linux, publish a Linux image, you need to create a separate definition. So that's how you can actually organize those images separately. That's about the hierarchy. Moving on, we want to talk about the sharing images at scale. So I mentioned about sharing, right? So you can share images at scale with RBAC sharing, wherein you can share it with an individual user, or direct shared gallery, wherein if you want to share it with other organizations, you can share it with the subscriptions or tenant ID directly. That way, all subscriptions in the tenant get access to that image. And then if you want to share it more broadly, and this is something that a lot of our open source customers actually use. They would directly share it with community gallery. That way, every user in Azure can access the image. So this is very popular among open source communities, institutions, large institutions, and universities, where a professor would want to share the image with the student community. They would leverage community gallery. Uh, so moving on, what are some of the best practices, right? So what are some of the best practices of Azure Compute Gallery? right? So you essentially have, as I said earlier, we support ZRS by default, block deletion before and now block deletion before end of life. Now there are some safety features that we offer to these, mainly because one so images sit upstream of VMSs. So essentially, if an image is deleted, it impacts thousands of VMs, which is why we care about images, and have a lot of safety features inbuilt into them, so that the images are not deleted at all, and the workloads are protected. That's why there's something called as block delete before end of life. So you can set a end of life on the image, and the image is protected, right? So that way, the image is not getting deleted before the end of life date. Similarly, there is exclude from latest feature that will allow you to safely roll out the image. So this is the SDP, I would say. In a way, you could set it to exclude from latest, and then the workloads will not pick this up. And then once you set it to false, that is when it'll be picked up by the workloads. Blocked region deletion, essentially, you can prevent accidental deletion from a specific region. So, for example, if you already published an image in all the regions, you can set that flag to true. That way, even if you delete it, the some of the regions that you've protected will not be deleted. And if none of these works, there's a soft delete feature which will allow you to recover. So even after all these, safety features, if the image is deleted, there's a soft delete feature which will allow you to kind of recover the image to protect to give you additional protection to your workloads. Now, why do we really need to automate and accelerate the image publishing pipeline, right? So I think, as I mentioned, right, it's not just about the image publishing; it's about how quickly are you able to roll out the image safely to protect your workloads, right? So every month, you see that the latest images are get published with the latest security updates. Now, you don't want to be in the business of like taking the image, adding customizations. You don't want to do that manually. And this is where AIB with along with Azure Compute Gallery come together, which will automate your end-to-end pipeline with CI/CD, end-to-end image publishing pipeline with CI/CD, and then finally, once the image is published, you have VM scale sets, and if you have auto OS upgrade enabled on the scale set, and it'll honor the your maintenance windows, and it'll based on the maintenance windows, the image, as soon as the new version of the image is published, VMSS recognizes that and updates all your workloads with the latest image behind the scenes. So just to give you that peace of mind, and making it a completely zero touch experience to automate your workloads, making it more secure. With that, I'll just conclude my presentation. I left you resources of what is Azure Image Builder, the templates in case you want to see how we can leverage templates to build your image publishing pipelines, and also some public resources about Azure Compute Gallery. Uh, Thank you very much for the opportunity to present this about this topic here. Thank you. I'm happy to take any questions that you may have. Yep.
Hey, Asta, sorry to interrupt you. Hey, when are you planning to share the certificate on email after conference, or is there any schedule? Okay, no problem.
Okay. Thank you.
Thank you.
Thank you.